Hello and welcome to today's webinar. This is the third and last public webinar of the Restore project. So we are happy to show you today some results from the 3 years of, or almost 4 years of research we've obtained so far within the project, and also introduce you the concept as well as assessment results and steps for further developing the Restore technology. My name is Thilo Walser. I'm from the Research Institute Solitis from Stuttgart in Germany. Our main role in Restore is to coordinate the dissemination and communication part. So I have the honor today to moderate this webinar today. One of our main research interests at Solitis is technologies that we consider as suitable for decarbonizing the heating and cooling sector. And Restore is for sure a very interesting concept to do so. So today the concept will be presented in the first presentation. Maybe you already have watched the first webinar recording where it was explained in more detail, and today there will be given a quick overview about it, as well as the potential applications of Restore, not only in the thermal energy sector, but in the energy sector in general. Furthermore, the Restore technologies has been assessed for sustainability, covering the aspects social sustainability, economic feasibility, and also environmental impact. And the results of those assessments will be explained today in 3 different presentations. We will also have a final presentation about the market overview and steps towards further developing this technology. Before we start with the first presentation, I want to inform you about some organizational aspects. We have a recording of this webinar, which is already started. And furthermore, we will have a Q&A section at the end of the last presentation. This Q&A section covers all the presentations that have been presented, so all the experts will be there in this Q&A session, and whenever questions arise during all of the presentations, you can use the Q&A feed, which is on top of the menu in Teams. So please, when you have questions, please post them there, and then we will collect them and answer them in the Q&A section. Also, we will have 2 Mentimeter sessions for getting your evaluations and estimations about the Restore technologies, and further instructions will follow during this this webinar. So this is it concerning the organizational issues, and we are now ready to start with the first presentation. It's about the Restore concepts and the applications as mentioned, and it will be presented by Francisco Cabello Nuñez. He's our Restore project coordinator, and he's expert in simulations, system simulations, concentrated solar power plants and thermal energy storage systems. Working at the National Renewable Energy Center of Spain, CENER. So I'm glad that you bring your expertise today in the webinar, Francisco. The stage is yours for sharing your screen.
Thank you very much, Thilo. I'm going to share my screen with the presentation. Just give me 1 second and let me know if you can see full screen. Can you see it?
We can see it in full screen now.
Okay, perfect. So first of all, thank you, Thilo, for your presentation. As Thilo said, I'm Francisco Cabello, project coordinator of Restore and a research engineer in the National Renewable Energy Center of Spain, CENER. And in this brief presentation, I will try to give you a general overview about the restore concept and some of the main applications of this concept. Well, so for this presentation, first I will give you an overall introduction to the project, just to set very briefly the context of this presentation and the context of the restore project. Then I will jump to the concept, first defining what we call the overall restore concept, then their main components, and also mention some of the advantages of this innovative energy storage system. And finally, I will discuss and I will give you some information about the most potential applications of this restore concept. So, well, before starting, just mention that the restore project is an European funded project, which involves 11 partners spread over Europe, and with the objective of developing a solution based on the combination of two key technologies. On the one hand, thermochemical energy storage, and on the other hand, the organic cycles to integrate sustainable energy sources and daily and seasonal energy storage solutions to ultimately increase the environmental, social, and economic sustainability of the district heating and cooling network. Well, so in the Restore project, we have as one of the specific objectives to validate the technology up to Tier 4, which is laboratory validation, and it's a relatively low tier level. So considering that, what we define in our project, first of all, is what we call the overall concept. And this overall concept, as we will see later, encompasses several potential applications. So, well, here in the screen, you can see the restore technologies, the main blocks, organic cycles, and the thermochemical energy storage. And as I mentioned, it's suitable for different applications, so we can take in account different energy sources that can be harnessed by our system, but our system can also provide energy to cover services to different users. Here in the energy sources, we classify them in three main groups: the high temperature heat group, where are included technologies as high temperature geothermal or concentrated solar, also high temperature waste heat. Then we have the green group, which is the electricity technologies, the technologies that produce electricity as PV or wind energy. And finally, we have the medium temperature group, which is suitable for solar flat collectors or geothermal energy or low temperature waste heat. All these systems can provide energy, and we use heat pumps that adapt the energy input, electricity, and the medium temperature heat to the conditions required by a thermochemical energy storage. Also, in the case that we have a high temperature heat that is suitable for application, we can directly integrate it in a thermochemical reactor. Well, the thermochemical reactor stores the energy in part of the energy can be stored for seasonal application. Another part of the energy can be used, that is in the form of sensible heat, can be used for daily energy storage. And when we want to discharge the system, we can provide high temperature heat for different industry, or we can also run an organic Rankine cycle that produce some electricity and especially adapts the energy to the conditions demanding for a district heating. So our system also provides at the same time some electricity and also heat to cover the demand of a district heating. Well, so as I mentioned at the beginning, we can identify two main innovative components. One is the organic cycles, and the other one the thermochemical energy storage. Let's take a look in detail to these components. Well, concerning thermochemical storage, mentioned that the system is based on a reversible reaction, where when we are in the charging phase, we apply heat to a component A and produce the component B and component C. And when we want to discharge the system, we recombine these components and we have an exothermic reaction where we release some heat. So the idea is that in our concept, we consider a reactor that works with oil and solids in suspension that are what we call the thermochemical material, here identified as A or B. So for starting the process, we have a flow that is rich in oil, and we mix it in a mixer with the product A. We flow this, and this is used, first is preheated, and then is used in the reactor. In the reactor, we provide some heat from the heat pump, and we have the thermochemical reaction where we release some product C, that in our case is water, and then we have a flow that is rich in the product B. Then this flow reaching product B is flows through the preheater, where it's released thermal energy, and then it goes to a separator where we separate the oil from the product B. We store the product B, and then we recirculate this oil. So that's the idea for the charging process, and for the discharging process, we have a quite similar process, but in that case, it's reverse. What we do is we add the product reaching B, we go through the preheater, we increase our temperature before entering the thermochemical reactor, and here we recombine it with the product C, that in our case is water. And in that case, when we recombine both materials, we have an exothermic reaction, which means that we release heat that can run the Organic Rankine Cycle. Then at the outlet of our system, we have a flow that is rich in the product A, and we circulate it through the preheater, and we go again to the separator, and we close the loop, storing the product A, and then recirculating the oil to start again the process. So that's the idea for the thermochemical energy storage. Within Restore, we have analyzed more than 10 different reactions that involves different product A's, product B, and C. But in general terms, where we identify more, most interesting reaction are those that are salt dehydration and irritation reactions that involve also the use of salts. And specifically in our system, we have chosen for the validation in tier 4 in a prototype the reaction based on the use of copper sulfate. Well, so concerning the organic cycles, mentioned that in Restore we also introduce an innovation in that part, and the first thing that we have to mention is that we differentiate between two different products. First one is a small scale system that is based on a fully reversible machine. When I said fully reversible machine, what I mean is a machine that is able to operate in the discharge mode as a heat pump, and when we want to discharge the system, we change the operation mode, and the same machine can produce electricity and work as an organic Rankine cycle. This fully reversible machine is based on the use of a screw machine that works as a expander and as a compressor, depending if we are in charging or discharging mode. And here we define a product around a maximum power input of 200 kilowatts electrical. This solution is expected to be a modular solution. So in the case that we have limitation of maximum power, we can stack several modules to increase the capacity of the final system. And also this solution is suitable for when there is a requirement of compactness because, for example, the system must be integrated in a building or this kind of applications. We can make the modules more compact in case, for example, we base our solution on heat exchangers as plate heat exchangers. So the other application that we have that is expected to be used in larger scale system is a machine that in that case is not fully reversible but mild reversible. What does it mean? Mild reversibility is that some components of the organic cycle of the heat plant can be also used in the other cycle that is the organic Rankine cycle. So part of the components, and mainly most of the heat exchangers, can be used for one purpose and for the other one. On the contrary, we have, for example, parts of the system that are totally different. This is the case of the turbo machinery. We identify we have the need of using two different turbo machinery for production of electricity or to use it as a compressor. We use a turbine for the Rankine cycle and a compressor for the heat pump. This solution is suitable when we have a higher power and we are in the range of application of electric megawatts, around 1 to 10 megawatts. We can also add some more power, but in that range. In that case, we expect to use cell and tube heat exchanger. So as this type of application, large scale application, are not expected to be directly integrated in buildings, what we expect is more, for example, integrate this kind of system in plants and that are somehow far from cities where there is plenty of room. We are not focused here on compactness. What we are focused on is on using shell and tube heat exchangers that allow us to have a higher efficiencies and a higher performance. So this is very briefly a general overview about the concept. Just let me give you some advantages of using this kind of system for storing energy. Is that the first one is that our system is in difference with other systems, batteries or other energy storage services. We can provide and store energy in both forms, the one hand electricity and heat, and this is a great advantage as it allows us to integrate different clean energy sources. For example, waste heat, but also electrical and thermal renewable technologies. The second point is related with the previous slide. Our concept is highly scalable. For example, in the range of small applications, we can think on our modular product that can be stacked in different modules in case of need of increase the capacity, and in case we need very large scale applications, we can move to the other concept where we can apply it for also applications which involves larger plants or industries with high consumption. The third advantage is that is also important to mention is that the system can be designed to provide daily energy storage, or also part of the energy can be used for seasonal energy storage. And it's suitable for storing large amounts of energy. In the case of the seasonal energy storage, it's important to mention that the part of the energy that is stored in the thermochemical form does not experience losses along the time, because we reduce its temperature with the preheater to ambient temperature, and we can spend a lot of time without important heat losses. That makes this part of the energy viable for long-term storage. More points to be remarked is that our system operates as I mentioned before, or turbo machinery of the screw expander that is directly connected with a synchronous generation. This generation mode is commonly used by conventional power plants, so it's commonly connected to the grid, and the grid is the operators of the grid are quite familiar with this kind of system. So this quality makes our system ideal for delivering grid support services. And the final point to be remarkable, especially when we talk about seasonal energy storage application where we need a lot of material to be used, is that the material that we are focused as a thermochemical material, when we reach the end of the system operational life, these salts, these TCM, that are dehydrated salts, are easily recyclable and reusable. When they are recombined with water, they return to their original state. So we can think even in resell this solution in the market. So I'm going to try, as I mentioned before, there is a lot of options in our framework to connect the restore system, considering different energy sources and different users, but I will try to give you a general overview of the main application of this system. Here I define 4 important groups. The first one related to the decarbonization of the industrial sector, then the provision of grid stability and ancillary services, the enhancement of the dispatchability for renewable energy sources, and finally thermal energy supply for residential consumers. Let's see in detail some of these main applications. First, mention that for the decarbonization of industry, we identify 2 main groups. The first group is industrial sector that works with higher temperatures, and in that case, the integration of restore will be directly connected if we have industrial waste heat at high temperature enough for run our thermochemical energy storage. And when we want to discharge the system, we can provide a high temperature for the industry, or we mark it as optional, but there is also the option if there is district heating close to the industry, or we have the intention of producing electricity. We can also add the Organic Rankine Cycle of restore to producing some electricity or some heat that is provided to the district heating. And this solution, considering that the high temperature industry are normally with high capabilities, high thermal output, and high thermal energy input, we consider that for this application is more suitable the large scale system of restore system. The other group related with the decarbonization of the industrial sector are industries that works with medium temperature. In that case, if the heat of the industrial waste heat is at lower temperatures, we will need the use of the heat pump that consumes some electricity. So our heat pump will exploit the industrial waste heat and also some electricity, or for the grid, or from a renewable energy technology that matches quite good with the profile of the industrial waste heat. That way we can reduce the buffers and increase the competitiveness of our system. And we store the energy, and when the energy is demanded, we can deliver it, or as high temperature heat for the industry directly, or as in the previous case, we have the optional case of producing some electricity and some heat for residential applications. In that case, we also consider more suitable the large-scale system, as industry normally works with higher capacities. The next application is supporting supporting the grid to provide stability and ancillary services. In that case, the restore technology is directly connected to the grid. We use the heat pump to consume electricity when the grid, is in a period of high production and low demand, and in that case we store this excess of energy, and for run the heat pump we couple it to a medium temperature renewable technology, as could be solar, which matches quite well with the periods that we have excess of energy on the grid, because also the solar thermal energy matches quite well with PV, that normally is the one that saturates the electricity grid. But also here, for example, we can include geothermal energy that has a flat production, and in that case we can exploit the restore heat pump when it's necessary for the grid. When there is a period where there is a high demand and low production, we can discharge our system to provide maximum electricity as possible. In that case, this solution can be suitable for both, for large-scale storage and small-scale modules, depending on the grid energy needs and also depending the specific locations. This is something that the grid must define. In case they need large capacities, we can go to the solution based on turbo machinery. In the case they only need small modules for increase the stability of the grid, we can use the modular solution. Quite related with the previous one, but in that case, the restore solution can be directly connected with the renewable energy source that produce electricity. In that case, the restore system is not connected to the grids, it is directly connected to the plant, the renewable energy plant. And in that case, it's quite important to have a good match between the technology that provides electricity and the technology that provides heat. For example, in the case we want to provide dispatchability to a PV plant, an excellent combination could be, for example, the solar flat collectors that also harness the global irradiation. And in that case, both technologies has a matching production. Or well, we can use wind energy combined with geothermal. In that way, we can avoid excess of electricity and avoid curtailments of this type of plants. And we will store the energy during high production periods and then deliver it when the demand is quite high. Also in that solution, we have the optional case of producing only electricity, or also provide services of heat to the different or well district heating or small buildings, depending on the case. As for this case, both the large scale system and the small modules are suitable depending on what we have in mind. If we have in mind large plants, in that case, we must base our solution in large scale system. But if we have in mind standalone solutions that are not connected to the grid, and we want to operate it in a standalone system, we can connect our small modules. And the final application is focus on providing mainly heat to buildings. In that case, we are talking about the small scale modular solution, and in that case we will allow, for example, buildings to reach zero emission or close to zero emission based on the use of our restore solution. So for example, in this kind of building, we can connect our modules to exploit some electricity produced by PV, and also harness the medium temperature heat or well from solar flat collector. Or if the building has, for example, is an university and it counts on a data center that has a waste heat, this can be also harnessed by our system. We store the energy when we have an excess, and then we produce mainly thermal energy for the building consumption, but also some electricity production that could cover part of the electrical building consumption. And I think that's all from my side. I hope to give you a general overview about the concept and give you some details of potential applications. And at the end of the session, I will be glad to answer your questions. So thank you very much for your attention.
Yeah, thank you, Francesco, for your presentation. It's very interesting and shows well the different applications of Restore. So yeah, we will now continue with the next presentation. It will be about the social sustainability assessment of Restore, presented by Angela Hahn from the Prospex Institute. Angela has studied social work in bachelor and intercultural conflict management in master. Prospex Institute, she's responsible for coordinating international research and innovation projects, and her expertise lies in the social dimensions of sustainable natural resource management. And she's particularly focused on qualitative research methods and stakeholder engagement. So happy to have you here, Angela, and the stage is yours.
Yeah, thank you very much, Thilo, for the introduction and also for the invitation to present the social sustainability assessment today. Let me quickly share my screen. Okay. Yes, so good afternoon, everybody, and welcome to the presentation of the Restore Social Sustainability Assessment. I will give the presentation on behalf of my team at the Prospex Institute. We from Prospex Institute are mainly responsible in the Restore project for the stakeholder engagement part. And one of our tasks is also to work on the social sustainability assessment. So before implementing any new energy technology at scale, it's crucial to understand not just how well it performs, but also how it affects the broader system around it. And that's why the social sustainability assessment, or the sustainability assessment as such, plays a central role in the Restore project. And we are not only looking at the environmental benefits, like reducing emissions or improving the efficiency, but we also consider economic impacts, such as cost effectiveness and long-term savings, and the social dimension, like the public acceptance, the safety, and the impact on the local communities. So taking all these three pillars, the environmental, economic, and the social pillar, into account, this allows us within the Restore project to build on a more holistic and balanced view of Restore's potential. In the webinar today, we will have like three different presentations in the different pillars. So today I will focus on the social sustainability assessment and give you some preliminary insights and learnings of our process. So the main objective of the social sustainability assessment in the Restore project is to ensure that the social dimension is considered in the technology's development from the very beginning on, to ensure a broader acceptance and long-term success. By doing so, we engage with stakeholders in an early stage of the project already to address the social concerns. And we are aiming, or one main objective of the social sustainability assessment is to provide a framework to assess qualitative social outcomes by identifying and assess the potential social impacts, such as health, safety, and well-being. And one main objective of the social sustainability assessment as well is to develop a framework or a tool for ongoing evaluation and further deployment, meaning that this framework and the overarching approach we designed in the Restore project could be potentially also implemented in different use cases. So let me give you an overview of the approach, the overarching approach of the social sustainability assessment within Restore. So we defined a 7-step approach, and we broke them down in different steps that we followed during the Restore project's lifetime. So the first step was the definition of the scope of the assessment, meaning that we defined our research questions, and also we worked on the definition of the overarching approach that I'm presenting right now. The second step was then to define the boundaries of the social sustainability assessment, meaning that we selected case studies that we implemented the social sustainability assessment on. And we also, beside defining the technical boundaries around these use cases, we also defined the social boundaries for the social sustainability assessment. We then delved into the definition of the categories and indicators for the social sustainability assessment to, in the next step, then select the relevant indicators together with partners that we then used for the actual implementation. In the 5th step, we then established the status quo, meaning that we were assessing the current systems in the use cases. I will go into further details later on. To then, in the next step, assess the actual implementation of the Restore use case, to then, in the last step, to do an analysis of solution and sustainability potential and needs, meaning that we did or we are still in the process of systematically comparing the status quo and the Restore implementation to then identify sustainable intervention needs, to then, in the last step, come up with recommendations for further actions. All of this is to show you the overarching approach, and to also share this important information with you that we are now in the final stage of the entire social sustainability assessment, meaning that we are at the moment finalizing the assessment of the Restore use case to then in the last step do the analysis of potential sustainability needs. This is why I'm going to share some preliminary insights with you today, but we are still in the last phase of our analysis. So the research questions that we defined for the social sustainability assessment are 2 main questions. The first is, what are the specific indicators to assess the social sustainability of the Restore solutions? And the second one is, are the developed Restore solution more socially sustainable than the status quo? As I mentioned before, we then selected 2 use cases. Francesco highlighted this in his presentation very well. So in the Restore project, we are working on 6 use cases. Some of them are large-scale solutions, and one as well is a small-scale solution. So we decided to focus on one use case in Italy, which is a small-scale solution, and one in Denmark, which is a large-scale solution. As I said before, the framework we came up with is meant to be implemented at one stage, or could be implemented to the other use cases as well. But for the selection and the implementation of the social sustainability assessment, for now, we focused on these 2 use cases. As I said before, the technical boundaries needed to be kind of translated into the social boundaries. This is why we selected the relevant stakeholders for these 2 use cases, and we did that based on the proximity level. So we came up with three main stakeholder categories: the workers, the surrounding community, and the wider public that can be affected or affect this, the systems we are working on. So the workers, the first level is the workers. They are involved in the construction and also in the monitoring of the systems. Then we have the surrounding community within a 1 kilometer radius, and then we have the wider public. After the selection of our stakeholders, then we delved into the comprehensive desk research on the social dimension of the energy system, meaning that we did a literature review, and collected all the relevant indicators and categories for social sustainability assessment in the energy sector. We then, based on the collection of the categories and indicators that we found in literature, we did then bilateral working session with project partners and the use case providers to select and validate the categories and indicators that are relevant for this specific social sustainability assessment on these 2 use cases. We then also did a survey and focus groups with the partners and the use case providers to assess the Restore solution and its implementation. So to give you further insights on the selection of the indicators table, as I said, we came up with a big database of different indicators and categories, and in a collaborative process with our project partners, we then decided to assess 10 main categories that we then divided into 24 subcategories to break them down into the indicators that we then finally assessed, meaning we had 70 indicators for the large scale, and not all of the indicators were also relevant for the small scale, so we ended up with a list of 56 indicators for the small scale. What we then did, we collected the data to assess the current system, and based on the data sheet, we then started the assessment based on the partner's perception. As mentioned by Francisco already in the introduction, we in the Restore project, we have a TRL level 4, meaning that the assessment on the social sustainability is of a qualitative nature. And so what we did with the survey and the focus group, we kind of asked partners to assess whether the system will change and how the impact will look like. And we used a color code for using the green color for a positive impact, the yellow color for a neutral impact, and the red color for a negative impact. This all was done to then kind of compare the status quo and to answer the research questions. Are the developed Restore solution more socially sustainable than the status quo? So to give you some preliminary insights and learning of the process, I will give you a quick overview of the 3 different stakeholder groups that we have been taking into account: the workers, the surrounding community, and the wider public. So for the small scale, we can say that in terms of risk of injuries, that Restore may not increase or decrease the current level of risk as the system operates at low temperature and low pressure, and there is no chemical hazards involved. As for the large scale, Restore may represent a slight negative impact in terms of injury risk compared to the conventional systems due to the use and the introduction of new materials such as copper sulfate. In terms of risk on health, we can say that for the small scale, Restore may not have any impact on air quality, temperature, and humidity, and it may have a minimal negative impact on noise since new components will be added to the system. As for the large scale, Restore is not expected to introduce additional impact and occupational risk, but it may have a slight negative impact on air quality because of odor, and but no impact on terms of noise. What is important to mention as well for the social sustainability assessment, that we deal with indicators that has slightly different natures. So we have one set of indicators that are directly related to the impact, but we also have some indicators that are related to the mitigation measurements. So this differentiation is taken into account when we do the analysis of our data. But here I will present them in the same slide because of timing, and it's a bit simpler. So in terms of the mitigation measures, we can see that for the small scale, additional trainings remains helpful, but not significantly increase like the need of training. So we have some personal protective equipment and emergency protocols already in place, and they need to be updated. That's how the system is going to change. For the large scale, the emergency protocols are already also in place, and additional targeted training is needed for workers to learn how to use the copper sulfate, so the new introduced materials, and no additional monitoring of noise, air might be required now. For the surrounding community, we can say in terms of safety, for the small scale, fire and explosion risk are low overall and manageable in industrial areas, and materials are stable with no major reactive hazards. For the large scale in terms of safety, there may slightly increase, risk may slightly increase in terms of fire and explosion risk due to the larger volume of the system, as well due to the flammable nature of the oil used, but not increased, like the likelihood will not increase in terms of evacuation. For the quality of living, in terms of water use, on the small scale, it depends on the decision if actually a closed loop will be used or an open loop of water. So the closed loop has a minimum impact on the quality of water. The open loop will increase consumption and contamination risk if it's not treated properly. In terms of quality of living for the large scale, restore may improve air quality by reducing biomass use. And in the event of a leak, it could negatively impact soil and aquatic life ecosystems. But the noise and the other levels remain unchanged. In terms of social acceptability, for the small scale, social acceptability will most likely increase, since social awareness in general will be raised. So, for example, an open day for students could be organized, or workshops around the restore technology itself. And for the social acceptability on the large scale, restore may have a minimal visual impact because the larger volume of the system. And in general, it could increase public trust by reducing energy costs. Finally, the wider public, for the small scale system in terms of local jobs and skill, there will only be limited new employment needed for the restore small scale installation, since the existing staff can already operate the system in their current roles. For the large scale, there may slightly boost the local employment by creating 1 to 2 new jobs, and with limited skills development needed to shorter training and already qualified workforce. As for the education and knowledge, in both cases, for the small scale and the large scale, the restore implementation would enhance hand-on learning opportunities for students, and more active involvement of the operation and the research. this is also the case for the large scale. And for the energy efficiency resilience, restore in the small scale may lead to slightly increased electricity use due to the convention losses. But if powered by renewable energies, it still contributes to reducing fossil fuel reliance and emissions. For the large scale, restore may positively impact the plant overall yearly efficiency, but will not be able to supply additional customers beyond those it currently serves. For the consumer benefits, restore on the large scale may lower long-term energy costs for households. So as I said before, this was a quick presentation into the preliminary insights and learning of the social sustainability assessment to give you an idea where we are at the moment. And as I mentioned before already, we are now in the final phase of the assessment. So we are still working on finalizing the assessment of restore use cases to then analyze or identify the sustainability intervention needs and to come up with clear recommendations to finally answer the question, are the developed restore solutions more socially sustainable than the status quo? With that, I'm coming to an end. Thank you very much for your attention, and I'm happy, or we are happy, to answer any questions after the first round of presentations. Thank you very much.
Yeah, thank you, Angela, for your great presentation and giving us some insights about the first dimension of sustainability assessment. We will now continue with the next part of the assessment, which is the economic feasibility. And for that, I hand back to Francisco. So please, the stage is yours. Francisco, you're muted still.
Now can you hear me?
Yeah, we can hear you.
I was talking with a mute microphone, sorry. Just give me 1 second, full screen. Okay, I think that everything is working now.
Yeah.
Okay, perfect. So I will try in this presentation, I will try to give you a quick overview about the economic assessment of the restore solution, the methodology, and at the end, some preliminary results that we have before ending the project. Well, this is the agenda. I'm going to jump directly to the introduction because we are quite tight on time. So first of all, mention that the economic assessment, we have the objective of evaluating the financial viability and cost effectiveness of our solution, of the restore solution, that at the end is an energy storage system. And in this analysis, we are focused on the analysis of the capital and operational expenditures, also potential revenue stream and key economic indicators such as the net present value and the internal rate of return. The economic assessment mentioned that is essential for determining if the energy storage system is viable in terms of economic, and also allows us to compare against other competitive technologies. And for this purpose, the approach chosen in the Restore project is focused on the figure of merit of the levelized cost of energy storage, adapted slightly, as we will see later, to the Restore particularities. Well, so first, very briefly, let me introduce and remind you all what's the levelized cost of storage. This figure of merit at the end is a metric that reflects the average cost per unit of electricity discharged from an energy storage system during its whole lifetime. What does it mean? The main idea that I want to transmit with this slide is that at the end, this figure of merit estimates all the cost and expenses associated to the system and divided by the total electricity that is discharged from the system during the whole system lifetime. And with this value, it helps us to compare. We have a normalized cost per each megawatt that is produced or delivered by our system, and allows us to compare with other technologies, as well as give us a first number to have an idea about the potential energy sale prices that can be reached by this technology. But something that is quite important to mention is that this approach is normally focused on energy storage system that consumes and produce electricity mainly, but also you can find some solution that consumes and produce heat. And in that case, we are talking about levelized cost of storage of heat. But there is a particularity of restore that must be remarked. If we remind or previously described concept, we mentioned before that the restore system not only consumes energy in one form, in the form of electricity or heat, it consumes energy in both forms, electricity and also heat. And at the same time, it delivers energy or it's able to deliver energy in both forms, as electricity or as heat. So this particularity has to be in mind for this analysis. So coming back to the previous slide, we are not focused in our case in the levelized cost of storage. We are focused on two different figures of merit. On the one hand, we define the levelized cost of electricity storage for our system. And for this calculation, what we consider is that we obtain some incomes from the discharged heat, the sales of the discharged heat. And when we want to estimate the levelized cost of heat storage for our system, we consider that there are incomes that from the discharged electricity sales. And in that way, we define these two figures of merit for our system, considering its particularities. Well, so what's the methodology that we follow to define it? First, we are focused on the definition of the CapEx, the investment cost. So for the estimation of the CapEx, what we have done is to define correlation based on literature and based also on the feedback on the industrial partners to have an estimation on the cost of the main components of the restore solution. For example, here we have a correlation, in that case associated to the non-reversible organic turbine, and we calculate a base cost, and depending on the correlation, we update this cost considering the CEPC index. Well, we use this procedure to estimate the cost of the main components of the system, the storage tanks, the heat exchangers, the reactor, the turbine, heat exchangers of the organic cycle, so on. And at the end, we have a summary of the cost of the main components of restore. Finally, we have a simplification, and we consider contingency factor 15 that is applying to the sum of all these costs of main components in order to estimate the final investment as a representation of estimation of auxiliary system, as could be control system or sensor of the control system, piping, also costs associated to the construction. So with this simplification, we try to increase slightly the cost to take into account this type of concepts. Well, so once the CapEx is defined, we move to the second part of the financial model, which calculates the cash flow for each year over the plant life. That is estimated around 15 years for our first evaluation. Once these cash flows are estimated in a model implemented in Excel, and we will see lately, the model concludes the relevant economic indicator as the net present value, the internal rate of return, and finally the main outcome of our interest, that is the levelized cost of storage for electricity and for heat. Here I bring also some consideration that these are taken account in our model. I'm not going to go very deep in details with that because we are tight on time, but just mentioned that for the inflation rate, our system allows to consider variable inflation rate, but in our first cases we consider constant. It also allows to consider degradation of the plant, assuming that percentage of the energy produced in the last years of the plant is lower. So we are able to modify this kind of parameters. For our first estimation, we consider low degradation. Also, we can define a schedule of the investing of the capital cost, and also to consider, for example, periods of contraction when there is no production, or periods where there is no working periods. And in that case, the hypothesis that we have, our system allow us to modify it. But for the first scenario analyzed, we consider 3 first years of construction of the plant. It will depend, of course, on the case and on the application that we mentioned before in the content, but this is just an hypothesis for the first calculation. And then we can also choose the amortization system, and in our case, we have chosen the French system. Well, we have our Excel that is plenty of rows and columns, so I'm not going to be in detail with the Excel. Just mention that the procedure that we follow is the next one. We in the Restore project have the IPSEGO platform, that is a simulation tool where we implement the use cases that were previously mentioned. And in these cases, we conclude the energy balances and we conclude the size of the different equipment. So we integrate in different datasheets in this tool the correlation that I mentioned before in order to calculate the components, the cost of the different components, and then this information is used in the Excel tool that I mentioned before. So we analyze, we receive the energy balances, which means mainly the electricity consumer, electricity produced, and the heat consumer and heat produced, and also the investment cost. And finally, our Excel conclude with the levelized cost of storage and levelized cost of heat, and also other ratios as the internal ratio of return and the net present value. Well, but considering that we have developed this model, but it's important to mention that as we have seen in the first session of this webinar, the Restore system is quite complex with a multitude of diverse applications, and each of these application set different boundary conditions that shape totally distinct economic frameworks, and it's not easy to deal with that. But what's our approach in the Restore project? Well, so in the Restore project, we define a virtual use cases already mentioned, that is at the end a virtual implementation of the Restore project concept for specific gas facilities over Europe. And in these use cases, we apply this economic assessment, concluding data, economic data as the investment cost, the annual cost, also the cash flows, and finally the levelized cost of storage for heat and electricity. There are 6 different use cases considered in the Restore project. You can check all the information of the use case in our website, but mainly they are considering different sizes, of course, and different energy sources and different users. So with these 6 different use cases, we expect to have different scenarios to conclude the competitiveness of restoring different applications. But unfortunately, the information of these use cases is not ready yet. It's not finished. We are still dealing with simulations. So this economic assessment cannot be applied yet. But for this presentation and to try to give you some numbers, we have defined general case and have some preliminary conclusions and some preliminary results related to the economic assessment. So I want to bring it here. First, mention that for the investment cost, when we analyze the restore solution and in the application for seasonal energy storage, that is the one analyzed here, something that is important to remark is the high impact that the storage material has in the final cost of the solution. Then we also identify that the organic cycles and also the storage tanks and the other costs are around 10 and 50%. And finally, that the reactor system, considering only the reactor plus the heat exchanger for preheating it, has the less expensive part, or is the overall system of restore that has a less expensive part, which is around 5 and 10%. And in this analysis, we also concluded very briefly some potential numbers or some potential estimation for levelized cost of electricity, of heat, and the internal return rate. Mentioned that for this we have considered positive scenario and negative scenario, 1 and 2. And the variables that were changing were, for example, the duration of the plant, the production of electricity, and some parameters that allows us to define this positive scenario and the negative scenario to conclude a range where the restore solution is. So for the levelized cost of electricity, we identify that there's potential to reach a low levelized cost of storage, approximately 0.08 in the best cases, and worst cases could lead to a higher levelized cost of electricity, around 0.2. Then we also define it for the levelized cost of heat, and we are in positive cases 0.05 euros per kilowatt hour produced of heat, and then we are almost in the double when we talk about a negative scenario. And in the internal rate return rate, we can be around 6 to 12 percentage of points of percentage for this ratio, which is interesting, but is in the line of competitiveness against other solutions. So what's the conclusion from here? We can be competitive depending on the scenario, that's for sure, but it depends strongly on the application that we define, and it's something that we will see in the future when we have the final numbers for the use cases that I mentioned before. So just to bring some conclusion for this presentation, I will try to summarize very quickly because we are out of time. I just mentioned that an extensive economic model has been adapted and implemented to estimate the main economic indicators, and that's quite good because now we have the tool to estimate different scenarios. And the next point, and also it's important to mention that these first results shows the relevance of the cost of the storage material in the economic assessment, and this variable represent a high impact in the final results. So these values must be considered and take in account with taking quite care. And then also mention that a reduction a potential reduction of the cost of the storage material will improve, of course, this favorability and maximize the competitiveness of the final system, restore system. So the next steps are carry out the economic analysis in these 6 different use cases. So I invite you to keep tuned to have information when we finish the evaluation of these 6 different use cases, and also have the final outcomes confirmation by the project completion by another project. But I hope to at least give you some details on what are we working on, and also some very preliminary conclusion and very general overview about the economic assessment. So thank you very much for your attention, and I will be glad to answer your questions at the end of the session.
The last aspect of sustainability assessment will be presented by Stefan Cristian Galusnyak from UBB University in Romania. Stefan has a PhD in chemical engineering, and his research focuses on advanced process modeling and sustainable energy systems, as well as life cycle assessment. He's also assistant professor at the Faculty of Chemistry and Chemical Engineering, and in Restore he worked on the environmental impact assessment. So happy to have you here, Stefan, and the stage is yours.
Thank you very much, Tilo. Just tell me if you see my presentation. It should work now.
It works perfect.
Okay, perfect. Okay, good afternoon, everyone. I would like to thank you, Tilo, for the nice introduction. Once again, my name is Stefan Cristian Galusnyak. I'm an assistant professor at the Babeș-Bolyai University of Cluj-Napoca, Romania. And today I would like to present some aspects regarding the LCA methodology and how we have applied the LCA to perform the environmental impact assessment of the Restore solution. As you may already know, life cycle assessment is a standardized methodological framework. It is utilized to determine and quantify the environmental footprint of a given process or product throughout its entire life cycle. This means that we take into consideration all life cycle stages, starting from raw materials extraction, manufacturing, transportation of a given product, its use phase, and also the end-of-life treatment. Now, I use this slide just to highlight one thing. So the main purpose of an LCA study is to quantify the environmental burden of a certain process, as previously stated. However, another goal of an LCA is to show which process or which stage exhibits the largest impact. Thus, one can act specifically in that direction. Now, to improve the overall performance, we must know the hotspots, and then we can act on those hotspots to reduce the environmental burden. Regarding Restore, it can be seen that residential and commercial buildings have a large influence. Thus, improving these steps, these stages, means that we may improve the overall greenhouse gas problem. Regarding the LCA methodology, life cycle assessment consists of 4 distinct stages according to the International Organization for Standardization. First, we have the goal and scope definition. Next would be the life cycle inventory step. Third, we have the life cycle impact assessment. And last but not least, we have the interpretation of the results. Okay, regarding the goal and scope definition, at this stage, it is important to state what is the goal and scope of the intended study. Then we move and we have to state what is the function of the investigated system. For example, the function of the system could be to generate electric and thermal power. Next would be the definition of the functional unit. The functional unit serves as a reference both for the input and output streams, and it is also used to easily compare different processes or different products. Finally, we have to define the system boundaries. Here we have to clearly state which are those processes that we take into account when performing such an LCA study. Depending on which processes we consider, our study may be classified either as, let's say, cradle to grave, if we take into account processes from raw materials extraction, materials manufacturing, the main production process, its use stage, and also its end-of-life treatment. However, if we go from cradle to gate, that means we should take into account processes from raw materials extraction, materials manufacturing, and the main production process. Another option would be to go from gate to grave. So it means that we only take into account the use phase and the disposal. It's an end-of-life treatment. Or we may focus on a gate-to-gate evaluation. This means that we only look at the main production process. Regarding the life cycle inventory, which is the second step of an LCA, at this point we have to account for all the inputs and outputs of the investigated system. We must consider all the inputs and outputs of each process from those included within the system boundaries. The data we use may be classified, as can be seen, either as primary data, which mainly comes from partners that perform experimental studies, or from industrial partners, or from experimental studies. Or maybe we may classify this as secondary data, which is primarily based on process modeling and simulation and literature data. As you may anticipate, we all would like to, let's say, build our LCA models only with primary data, raw data. Yet in those certain times when primary data is not available, we must look at process modeling activities and literature studies. In terms of life cycle impact assessment, so the third step of an LCA, this may be done by using different software, such as OpenLCA, CIMA Pro, and so on. The one we use is called LCA for Experts. It was formerly known as Gabi software, and it is developed by the Sphera Solutions. Same applies when choosing the impact assessment method. So there are lots of impact assessment methods that may be used. I'm thinking about RECIPE method, CML, Eco Indicator 99, or others. Here in figure 2, you can see the general structure of the RECIPE impact assessment method. As you may see, the impact assessment may be conducted either at midpoint or at endpoint level. Now, midpoint impact categories offer more accurate results, while endpoint indicators are, let's say, easier to understand. Now, when selecting RECIPE, there are also 3 cultural perspectives, each having its own characteristics. We have the individualist, which is based on a short time span. Next, we have the hierarchist, which accounts both for short and long time span. Let's say this is the default model, as it is based on scientific consensus. And we also have the egalitarian, which assumes an extended lifespan. The hierarchist perspective stands as the most common and balanced perspective. Thus, it is the most widely used when looking at LCA studies. Here we have a description of several midpoint impact categories and the main impact contributors in each case. We have the global warming potential, which is characterized by anthropogenic emissions leading to an increase in surface temperature. As main contributors, as we all know, we have carbon dioxide, methane, chlorofluorocarbons, and so on. I would also look to the human toxicity potential category, which is divided in human toxicity potential cancer and human toxicity potential non-cancer. Those two are characterized by risk increases of cancer and non-cancer, respectively. And as main contributors, we have chemical substances toxic to human health. Okay. So that was all I have prepared about the methodology. Now let's take a look at the RESTORE prototype. First of all, this study is a cradle-to-gate LCA analysis, as we took into consideration raw material supply up to the main charging and discharging processes, and we went downstream for waste disposal. Here I would like to point that with the help of our partners who worked and developed the charging and discharging models using the IPSEGO platform, so we went from these two models to the following. This is the LCA plan for the charging cycle. This would be the LCA plan for the discharging cycle. We developed an LCA model which accounts for all the inputs and the outputs, along with certain assumptions that we had to make. Now, if we zoom in every single box, we would see something like this. So on the left-hand side of the slide, we may see the TCM charging, so the charging box. On the right-hand side, we may see the Novec production, while the other one is referring to the electricity generation. So we have here a space where we can define certain parameters, maybe perform certain calculations, such, for instance, maybe we would like to go from a mass flow rate to a molar flow rate. We can perform such calculation in the parameters section. Afterwards, we have the inputs and the outputs. We should carefully select the streams when defining the input and output streams, as they might significantly influence the outcome of the analysis. One very important aspect regarding the RESTORE prototype, and I'm going to emphasize later on this, is the LCA plan for the RESTORE prototype construction. Now, when going through the LCA methodology, I was talking about primary and secondary data. So even though Novec is widely recognized, there are very few information regarding its production process. Therefore, me and my colleagues had to go through several literature studies and find how Novec is chemically produced. This would be the LCA plan for the Novec production. Following the same reasoning, we have in here the LCA plan for the copper sulfate production and also the LCA plan for the oil transportation. With regards to the LCA results, to assess the environmental sustainability of the RESTORE prototype, we performed the calculations using RECIPE impact assessment method, following the hierarchist cultural perspective. The functional unit was set to 30 kilowatts power. As can be seen, the largest impact scores are registered in terms of global warming potential, human toxicity potential, non-cancer, and also terrestrial ecotoxicity potential. In the next slides, I would like to take a look at those three impact categories. So in terms of GVP distribution for the overall system, we may see that the oil production, so the charging system, has a contribution of 9.51 kilograms of CO2 equivalents, while the Novec production contributes by 5.42. Now, if we take a closer look to those two subsystems, we may see that the oil production has the largest contribution in the charging cycle. The discharging cycle exhibits negative impact due to the electricity and thermal power generated, while for the Novec 649 production, we can see the chlorine, which exhibits the largest impact. Same when looking at the human toxicity potential non-cancer distribution, one can see that the largest impact comes from the restore prototype construction, and it is followed once again by the oil supply chain. Going into further detail, it can be noticed that copper production exhibits the largest influence when referring to restore prototype construction. However, it is important to state that it's not the restore technology itself. It is more related to how copper is produced, since we use copper for wires and so on. So it's not the restore technology itself. It is more about how copper is produced, how you produce stainless steel, and so on. Okay, same thing when looking at the terrestrial ecotoxicity potential distribution for the overall system. We can see that the restore prototype construction, thus the way we obtain copper, stainless steel, and so on, exhibits the largest impact. We have the copper production once again for the restore prototype construction, while when looking at the Novec 649 production, we may see that the hydrofluoric acid followed by chlorine rank as first and second contributors. Now, to sum up, I would like to say that global warming potential, human toxicity potential, non-cancer, and terrestrial ecotoxicity potential exhibit the largest environmental impact scores. When looking at the charging cycle, the oil supply chain ranks first with over 80% of the total impact score. Therefore, any improvements in this direction would considerably lessen the environmental burden. About 85% of the human toxicity potential non-cancer impact may be attributed to how copper is produced. This is because copper is further used for the restore prototype construction, and the main construction-related risks are associated with the upstream production of the materials, copper, stainless steel, and so on. So it is not related to the restore technology itself. Recently, me and my colleague Alessandra, we attended the iChip conference to present more information regarding the environmental impact of the restore prototype and the restore solution. In the next month, I think there should be a scientific paper where everything is explained in much more detail. This is our team, our professors, my colleague Alessandra, and me. Thank you, and I hope there are more things that you better understand now about LCA than at the start of this meeting.
Yeah, thank you, Stefan, for this interesting presentation and for concluding the sustainability impact assessment. So now we will have the last presentation of today's webinar. It's a market overview and roadmap towards the further development of Restore, and it will be presented by Lucia Hörner from the Steinbeis Europa Zentrum. There she is project manager for innovation processes, and she has background in international innovation management and bioeconomy. She's responsible for organizing the further use of results from Horizon projects and assesses user needs and product market fit. And with those tasks, she was also involved in the restore project, and will show some results of the market overview and of the roadmap. So happy to have you here, Lucia. And yeah, the stage is yours.
Thank you, Thilo. All right, so I will give you some insights on what's happening outside of Restore and what is the environment influencing actually where we want to operate with our Restore technologies. And to start off, I mapped the connections between the 4 key results we have in our project, which have been also nicely presented already. So we have the thermochemical energy storage, which integrates into the organic Rankine cycle systems on the big scale and small scale level, so for different applications. And then also findings from small scale applications can feed or provide knowledge for big scale applications. So these are the Restore technologies as we have them, and they are being simulated with the help of our process and component models in our virtual tool, which is operated on IPSA-Go. So the thermochemical energy storage design, I have here always the kind of a value proposition that our solutions are offering, and they go hand in hand also with the applications that were presented by Francisco earlier. So I'll keep this introductory part a bit short and focus more maybe on the aspects that link to, well, who will be customers, who will be key partners in this process. So for this result, we are targeting energy-intensive industries, renewable energy producers, and utilities, grid and district heating, cooling network operators. What is quite special here is that we also see engineering, procurement, and construction companies, as well as energy service companies, somehow as like entry points for also reaching further customers and other partners that would be relevant for the further development and a potential bringing this result closer to market will be heating, ventilation, and air conditioning equipment manufacturers, as well as manufacturers of energy storage systems. Regarding the market size for this result, here we are actually targeting the market of thermal energy storage, specifically the one for seasonal and long duration applications. This market is or has been projected to be at 4.3 billion euros 2 years ago, and is projected to be around 8 billion euros in 2030. However, it's quite difficult to get concrete data for the thermochemical energy storage market, which is a share of this market. And so the number I'm showing here, this is pretty much the market for 3 different types. So for thermochemical, sensible heat, and latent heat. And it's a bit, it's a bit difficult to get concrete data. But it's some studies suggest that the share for thermochemical energy storage is among these 3 is the smallest. However, it's really continuously growing, and also as we're expecting cost decreases for thermochemical energy storage due to technological advancements, this will for sure also further drive the market increase here. There's a rising need for grid balancing, renewable energy storage technologies, as well as integration and industrial decarbonization that is, together with climate policies and energy storage incentives, very strongly providing a case for our technologies that have been developed. Then we have the large-scale reversible thermodynamic process. So this large-scale application, which is the most effective for really maximizing renewable energy and waste excess heat utilization. Here, target customers are district heating and cooling network operators and energy-intensive industries. And our key partners here are Tor Borden, who is a partner in this project, as well as district heating, cooling utility firms, industrial equipment manufacturers, and also technology integrators. What I can mention here is that it's quite adaptable and flexible. These are some terms that you'll also see for the small scale, as these are really value propositions that are not just linked to an individual result, but they're it's something coming up across all the various restore technologies. In terms of a market size, there's a large but immature market for decarbonizing district heating and energy-intensive industries. We see a larger, or like 2/3 of the temperature demand is more for district heating applications, while about 1/3 is for temperatures higher than 100 degrees centigrade. And this is relevant for industrial process heating. We found some information that approximately 245 million tons of oil equivalent of waste excess heat is available for recovery in the EU. This is nearly equal to the EU's total energy demand for heat and hot water in residential and service sector buildings. So just to put this a bit into context. And also here, the EU decarbonization policies, urban development, and sustainability goals are strongly driving the market for this type of application, and also the adoption of this technology. It's influenced by equipment costs, of course, energy prices, and depending on the risk tolerance of industrial sector. Our small-scale application, here we're targeting educational and research institutions, local utilities, and small municipalities, as well as industrial parks and technology campuses. Our core partner here is Enabasc, and other partners which will also be needed for the development and for the cooperation is academic and research institutions, local municipalities, and technology park managers, as well as a strong buyer-supplier relationship is important, as we're still developing the results together with also the partners with whom we're cooperating. So in terms of market for this for this result, we have about 1,500 higher education institutes with engineering programs in Europe, between or just below 400 technology centers, and cities of a size where this type of solution could be applied is around 60,000 in Europe. So this is the kind of market for our small scale application as we see it right now. We have a rapid growth in renewable energy technologies, and also the strong demand for flexible flexible small scale systems that can also fit to the need of also smaller towns, where the energy can be then managed locally. And our fourth key result from the project is our simulation tool, so the virtual tool, which is built on the restore process models based on restore technologies. So here, key customers we're addressing is engineering, procurement, and construction contractors, district heating, cooling operators, renewable energy system developers, and also technical consultants of a smaller size because of the various added values that this simulation tool offers, and it's really now very well fit for showing or allowing this virtual simulation without the need of physical piloting based on the restore technologies. So it helps to reduce costs, definitely mitigate risks, and have a very effective planning. Also here, there were some messages shared in the chat. If you want to learn more about the simulation tool, there's several options. Our key partner here is SimTech, and then also academic teaching staff and researchers and renewable energy system developers are relevant also for the further cooperation. Our total addressable market in Europe is about 5,000 users, while we're expecting that 10 to 15% is what is realistically servable. And we see a very strong increase in simulation software market, which is influenced by, in general, the digital transformation of EPC, consulting and energy system design sectors, also compliance requirements and considerations in terms of sustainability strongly influence this market. Now I'll present the two market segments that are the most overarching, let's say, so district heating and cooling. Some figures we found here is that it's projected to grow from around 220 billion euros in this year to almost double, or to actually more than double by 2033. So in 8 years. So there's a very strong share of or a very strong how to say it. I guess we're targeting the right the right market here. This growth it's driven by urbanization and densification of cities, government incentives for renewable integration. Also environmental regulations that target carbon neutrality, and technological advancements in smart grids and low temperature networks. We have right now more than 15,000 district heating cooling networks operational in the EU, and also a lot of new households. 8.5 million households are expected to be connected in Europe within the next 5 years. Europe is a global leader in terms of district heating, where the countries with the largest use for residential areas is Sweden and Denmark. The policy influence is shaped by Repower EU initiative, and upcoming heating and cooling strategy is expected to have an influence here. We see a strong increase also in terms of the district heating and energy being fed by renewables and waste excess heat. So this is also a trend that goes in line with our project work. However, barriers remain regulatory uncertainty, which is of course bound also to national borders, and the willingness to invest in large scale infrastructure with very long payback periods. For energy-intensive industries, which includes, for instance, cement, steel, glass, chemicals, food and beverage applications, here we have high thermal demand. On the other hand, it's difficult to reduce emissions. We have we see in the overview, so steel and metal, as well as cement and ceramics, is the largest among these the sector, so we also see that there's a shift from heat-driven to electricity-driven processes, supported by electrification, among others. In terms of waste excess heat, so more than 300. We have approximately 10% of the EU's total energy consumption in industry, which is available right now for energy recovery or for heat recovery. So that's a large share on what is already available today. However, challenges are lack of concrete data on the waste heat sources, also awareness in some cases, high upfront investment costs, the long payback periods I mentioned already, regulatory aspects, and integrating new systems into the existing plant processes. Within this project, we have conducted a PESTEL analysis, which looks at political, environmental, economic, social, technological, and ecological factors influencing the market of our restored technologies. Here we see that the policies are very strongly influencing our the policies promoting decarbonization, energy efficiency, and renewable integration are very much supporting our developments in the project. That government stability and policy continuity are essential, especially for long-term investments. In terms of economic factors, here all the solutions we've developed, they're very sensible to energy prices, inflation, and the broader economic climate, while rising energy costs actually enhance the value proposition of the energy saving and storage technologies that we have. Economic viability is a key adoption driver, and also sustainable resource management is key, as we've now seen in an earlier presentation, that more than 50% of the system costs are actually linked to like storage materials. So really making sure where you get the storage materials from, and also here's some like practical aspects on the supply chain are relevant. The social factors, so here I guess it's also linked to political climate in terms of acceptance on certain technologies. In general, we've observed a growing stakeholder acceptance and a social demand for clean, sustainable energy source solutions, which also promote a local energy autonomy. And however, that a lack of understanding of the technologies can hinder the widespread adoption, or in general the uptake of the solutions. In terms of technological factors, there's a rapid there's a high speed in the technological development, strongly also integrated, influenced by AI integration, automation, or advanced advanced protocol systems. And environmental factors are strongly in favor of our solutions, while something like the recyclability of materials is something to be considered, and has been considered in this process. Also for instance, the effectiveness of the system, it depends on the availability of renewable energy sources. So that is indeed a factor that cannot always be guaranteed. So it really depends on where then, for instance, a large-scale application is to be realized. Legal factors. Here, I'll also make a reference on the next slide. The compliance to EU and national regulations, including safety, emissions, and energy standards, is very important. And just this year, there has been a new European F-gas regulation with a quota system increasingly limiting imports and production of hydrofluorocarbons. And it's foreseen to eliminate their use by 2050. So this is also an environment that's constantly developing and changing. So this is why, for instance, in this project, our colleagues from TUR Boden, they have taken a closer look at the regulatory environment and standards influencing our restore technologies. And this is a public report I'd like to draw your attention to. It's available on our website, and it sheds light on 3 European directives: the Energy Efficiency Directive, Renewable Energy Directive, and the EU Taxonomy Regulation, which are influencing our technologies. And then it shows clearly, okay, how is the influence? Is it in a positive, neutral, negative? And some further clarification on how it actually affects the technologies. And in general, these directives, they encourage investment in energy efficient and renewable technologies, set clear targets and definitions that guide project design and implementation, provide access to funding, and also create compliance obligation. So yeah, they're providing this frame for the wider adoption. And this will be actually my last slide. We have recently discussed in the project what will be the further development steps, how are we going ahead, and we see an overall tendency that well, we haven't developed a commercially ready product. We have a technology readiness level of 4. So there's still lots of work to be done. But some aspects that have been mentioned is, for instance, that we want to further research on the operability and scaling of the reactor. So this is in terms of the thermochemical energy storage, or assess economic application scenarios, also for a potential larger scale demonstration. We want to conduct lab tests of subsystems and early system configurations in terms of the large scale application, refine system design, and then also based on this test feedback, and develop prototype tailored to the early adopters. So this can be relevant for both small and large scale, and also for the small scale and advanced prototype development and pilot testing will be logical next steps. While for the Restore Virtual tool, first of all, we want to create and validate for the test cases. That's why also we invite you to have a closer look at our virtual tool, and then ultimately, of course, enhance also the process model, our library with the process models in line with the technological development of our solutions. And aspects such as tailoring our really concrete products to the needs of individual customer groups, identify early adopters with whom really like concrete pilot projects in a larger scale can be realized, funding, securing funding, formalizing agreements. These are like more business related aspects that go hand in hand with the technological development. So I'll leave it at this point, and hand then back to Thilo. Thank you.
Yeah, thank you, Lucia, for this great last presentation. And I think there are definitely options on the market to integrate the restore concept, and there will be use for it. And I'm sure that further research will bring the restore technology closer to the market. In the meanwhile, I want to announce just an event that will be having soon, so you can already save the date for our final restore workshop. It will be month of September. That's also the month when the restore project will end, and the final workshop will be in Vienna. Vienna is the Technical University of Vienna is the place where the restore prototype is assembled and that's also being tested. So this workshop will include a visit of the restore prototype and also roundtable discussion and presentation of the final project results. So we invite you to this on-site event, and invitation with details how to register will follow soon by email. And you can also stay updated with our LinkedIn site and also on our website to don't miss the event invitation or any other news. Also, I invite you to join the user community. The Restore virtual tool has been mentioned several times during this today's webinar. So if you want to try out the virtual tool in ipsigo and follow the use case calculations as well as try modeling the restore integration in your own use cases, then you can with this QR code enter the form and join the user community. It's for free, and you will receive 90 days free trial access to the tool. Okay, so I think no questions have been posted. Then we can also close today's webinar as we are already over time. I want to thank all of the speakers for their today's presentations and the time and giving us insights about the different aspects of assessment as well as applications and the market overview. And I also want to thank all the participants for staying until the end and for following the presentations. I hope you got some insights of the research results that have been obtained, and stay updated about the project. And also, if you want to reach out to the speakers, don't hesitate to contact us, and we will be happy to get in contact or meet at the final workshop in Vienna. So I thank you everybody and wish a nice rest of the day.